let's go ahead and let's do an example of, introductory example to design, show you how this might work. Let's say we had a beam that was 12 inches wide and has an effective depth of 20 inches. Say it has an F prime C of 4 KSI, has an FY 60 KSI, and let's say it's supposed to carry a factored moment in MU of 200 foot kips. And our problem in this design will be to design the steel. So design the area of steel and then choose the number and the size of the bars that we're going to use. Now before we get started, the one thing that I would urge you is to watch your units when you do this. Anytime you use these tables that'll have K-bar versus row, you got to make sure what type of units they're using. Okay? And I mean generally if your K-bar value is 100, 200, 600, 700, and something, it's in PSI. All right. If it's in if it has a value of 0.4, 0.5, 0.8, it's in units of KSI. But check to make sure of that. And as you're doing this whole process, just watch your units. Make sure that you're not mixing feet and inches and all that stuff. All right. So, how would we do a problem like this where we have to design the steel? Well, we start out with the formula that we had before. Our design capacity has to be at least equal to MU. We can write our design capacity formula, as we talked about earlier, like this. MU in this example is stated to be 200 foot kips. We know what phi is. We're in a beam type problem. Phi is going to be for bending moment 0.9. We know what B is. Again, we're giving you a sort of a lockdown design problem, so 12 inches. We know what D is, 20 inches. So I can rearrange this and solve for the K bar, which is a function of reinforcement ratio Fy and F prime C that I would need. So 200 foot kips divided by phi, which is 0.9, B, 12 inches, and D, which is 20 inches. Remember, D is square. Anybody got something to tell me here? Units, feet, up here, inches down there. I better multiply this by 12. Put this into inch kips. K bar value that I would come up with is going to be what? 11. Okay, I can't hear.
Oh, sorry.
0.555. Again, if you look at the units, I mean, this becomes inch kips. This is inches cubed. So this unit down here is actually kips per square inch. Now, 0.555 KSI is the same as 555 PSI. That's what, I was sort of saying. You got to, if you're given tables, you just got to make sure you're, what units you're dealing with. So, for this problem, we go to tables. Again, like I said, tables could be found in the back of the book. In some books, they might actually put them in the lesson or in the chapter that you're dealing with. We've got a problem here where F prime C is 4 KSI and Fy is 60 KSI. So you just got to find the right tables that you're dealing with. So up on in this book I have in front of me on page 492, but again it could be in the middle of a lesson or middle of a whatever. I've got the table that I'm dealing with, right? Because it says 4,000 concrete, 60,000 steel, right? Got it? Okay. I'm going to look for a K bar that's, at 555 PSI, or in this case, 0.555 KSI. So I look down through these tables. I see a value that's at 0.5569. And the corresponding row value is what? 0.0102. So I go from here, I go into the tables, and I pick out a row value that's 0.0102. And if you're using these tables, you're not going to find, rarely would you find something that falls exactly on what they have in the table, so you'd always probably go to the next one, the one that's higher. Okay? So you got a row value of 0.0102. We talked about this last week, we talked about it earlier. Rho is equal to the area of steel times BD, or the area of steel could be written as rho times B times D. .0102, B is 12, and D is 20 inches.
2.448.
And what was it, please?
2.448.
2.448. So area of steel is basically 2.45 square inches. So for this beam that was 12 inches wide, had an effective depth of 20 inches, had F prime C of 4, and Fy of 60 KSI, you're going to need an area of steel of 2.45 square inches. Now the question comes up, you got to choose the number and the size of the bars that will work. Okay, so how are you going to do that? What's that?
Rebar chart?
Yeah, I mean, you go to your rebar chart. Again, different books and resources will have different things, but I mean, you can do this just knowing what the area of steel one bar is. I mean, I know the area of steel of a number 9 bar is 1 square inch, so I could say, hey, I could use 3 number 9s. That would give me 3 square inches. That's greater than that. That's fine.
That's what I chose.
Okay, so that works. Could you use 3 number 8s? No, it falls just short. 4 number 8s, well, that's a possibility.
One number 18.
You use 1 number 18. It might not be good, but 3.16. What about,
I say 6 number 6s.
okay, 6 number 6s. What's 6 number 6s?
It's 2.64.
Would you ever take one from, take like a 14 and then
No,
a 5?
no, you want to do that.
What about 5 number 7s? Would that work?
Yeah.
A number 7 bar is what, 0.6 inches? So that's 3. So I mean, you know, you've got possibilities there. You know, you might say, hey, let's you know, everything's in weight, so the lower area that still works would be okay. It'd be less weight and whatnot. The problem with this might be trying to fit these bars in a single layer. I mean, you know, when you start getting double layers and you start doubling up or even triple layers, the work that it takes to actually build the cages and whatnot is a little bit more intensive. So, you know, you might say, hey, let's choose 6 number 6s. You might start thinking about, can 6 number 6s fit within 12-inch wide beam?
When you start stacking, can you change sizes, pulling up?
You can, but I mean, generally they don't like doing that. Okay, it just gets too confusing. There's room for errors. Okay. Yeah.
Does that include the multiple layers? Like if you had 2 layers, each of them was 2.45?